Ladies and gentlemen, class recording is started. So, yesterday, we started talking about the relationship between magnetism and electricity, and we talked about how a current flowing through a conductor causes a magnetic field. And sort of by accident, our Danish scientist Ørsted notices that if you have a current-carrying conductor around other magnets, things like compasses, you will see a change in their behavior. That when they interact with Earth's magnetic field, they line up so that the north pole of the magnet faces the north geographic pole, right? We learned that on Wednesday. But if they interact with other magnetic fields, the orientation of that magnet can change. What he realizes is that a current passing through a conductor near a magnet will change its orientation. The only way that can happen is if it makes a magnetic field. And so then we talked about the right-hand rule and how that shows you that which way that the field lines are drawn, that if you put your thumb in the direction that the current is flowing, and you curl your fingers around that current, or the wire that's carrying that current, you will see circles, the arrows point in the direction of your fingers. But if you take that current-carrying wire and you bend it into a circle, so here, right, if you look at this, right, if the current was flowing to your left, my right, through a conductor, the field lines would go like this and they point to my face. But if I take that wire and make it into a circle, it still flows the same way, but now as it goes up here, right, fingers still pointing towards my face. And as it goes through the top of the circle, fingers still pointing towards my face. And as it comes down the other side of my circle, fingers still pointing towards my face. So that ends up with the magnetic field always being oriented the same way. And now our current-carrying wire behaves very similarly to a bar magnet in that the field flows from one side to the other and it's always the same side. And if we put more than two current-carrying wires together, we get two bar magnets. And if 2 is better than 1, 3 is better than 2, and if 3 is better than 2, 4 is better than 3, and we end up with what we call a solenoid. That solenoid is a coil of wire that is wrapped into many loops. The more loops that you wrap it into, the more magnetic fields can be produced. But only if what? As long as there's current. If there's no current flowing through this wire, it doesn't do anything, right? That's why it's referred to as an electromagnet. Because unless there is current, unless there are electric charges flowing through it, it does not create a magnetic field. Good there? Okay. Let's transition to today's outline. Don't worry about the galvanometer and the electric motor on the back. That's just application stuff, so you won't be responsible for that. All right, let's go here. Good. You notice my festive holiday background theme? Yeah. I like it.
I like it. It's like a Mardi Gras.
Mardi Gras is usually more like purple and yellow.
It's like watch another video.
Okay. The picture that shows up here on the board is technically a solenoid. The red and black parts here in the middle, this is just a coil of wire that has been wrapped around probably a wooden core, right, several times. And using the plugs, or that the guy in the video yesterday called them crocodile clips, right? You usually here in America we call them alligator clips, but Britain, I guess you call them crocodiles. Anyway, this device that it is attached to is an ammeter. An ammeter measures what?
Volts.
Nope.
Amps.
Current. It measures amps, right? If you just connect the solenoid, the coil of wire, to an ammeter, it won't measure anything. Current doesn't flow through a circuit unless there's what? Which is a voltage source. Okay? A battery is a voltage source. And we said that a battery provides what to our circuit? Electric potential energy. Okay? Current won't flow unless there is a source of electric potential energy for it to flow from high to low. However, in the picture, this guy is holding a bar magnet. And if you move the bar magnet in the vicinity of the coil, you will measure current flowing through the coil of wire, even though there is no voltage source. Because those charges, right, interact with the magnetic field that is created by the magnet, and the movement then is created because of that. Somebody earlier today said, well, if voltage is a source of electric potential energy, does that mean that there is magnetic potential energy? And the answer is, yeah, right? Anything that has a field can have potential energy, right? We live in the gravitational field of the Earth, and we have gravitational potential energy. Electric potential energy exists around electric charges. Magnetic potential energy would exist around a magnetic field. So now, right, those charges are moving not to go from high electrical potential energy to low electrical potential energy, but to go from high, I guess if you want to think about it this way, magnetic potential energy to lower magnetic potential energy. Good there. Okay. So, this idea that a magnetic field can cause currents, even though there is no voltage source, we refer to as electromagnetic induction. That an electric current can be produced in a circuit by a changing magnetic field. We call this Faraday's law. Right? Faraday gets credited with the field theory, right? The fact that the magnetic field can cause movement of currents is Faraday's law. Now, here, right, first you need to have a loop or a complete closed path for charges to flow. A closed circuit, right? If you just have a piece of wire, you won't get charges flowing through there because they don't have anywhere to go to get to a lower energy. So you need to have a complete loop. The only thing that's missing is you don't have a voltage source to cause those charges to move. They move because of the magnetic field. So, as long as you change either the position of the circuit in the magnetic field, or if you change the magnetic field itself, you can get those charges to start moving. So something has to change in order for the current to be induced. Yeah, this is deep, right? So a current can be produced by rotating the circuit or changing the magnetic field. So you have to change something in order to get those charges to start moving. Good there. Now, the next slide, I'm not really going to hold you. You're not going to have to really apply this or draw it on the test or anything like that. But it's going to be important to explaining something a little bit later. So, a current is only produced when the conductor moves perpendicular to the magnetic field. And again, I'm not going to make you draw a picture of this on a test, or I won't even show you this, but it will be important to explaining something a little bit later on. So the charges have to move in a way that is perpendicular to the magnetic field. That's the only way that they experience force, and that's what gets them to move, or causes the current. All right, good there. I'm going to, all right, I'm going to jump ahead a little bit. I'm going to jump onto the back side, and then we'll come back and finish the front side because we'll talk about the recip, right? So I want to show you a picture of an AC generator. Okay. I used to have one of these, but it broke last year, and so all right. Somebody broke it. Somebody was messing around with it and didn't use it properly, and they broke it. So, shall remain nameless. So they don't need to shame. So, yeah. I was not happy. So. All right. Up on the board is a AC generator. So, over on the right-hand side, there is a crank. And it is attached to an axle inside, but inside is a coil of wire, just like we looked at before, a loop. It's a complete conductive path. The outside part, these black things right here, these are magnets. So inside of those horseshoe magnets, there is a magnetic field. If this crank is attached to a coil of wire inside, and we turn it, we will see current that flows through the coil of wire, the closed conductor. That coil of wire is attached to these two wires out here, which are attached to a light bulb. Looks like a Christmas tree light, but it's still a light bulb. Okay? So what we see as we turn this crank with our hand, the light will go on and off, and on and off, and on and off, if we turn it slowly. If we turn it quickly, we can see a continuous light. There's also an example of this. If you've ever been to the Science Center downtown, they have it's like you sit on a bike and you turn the pedals and you get the lights to light up. Like there's like a light, and how fast you turn the pedals gets how many lights to light up, and it's bright and stuff like that. Same idea, except that instead of your hand turning this crank, your feet are turning the crank. But it's still turning a coil of wire inside, and there's a magnet on the bike underneath, so you're turning this coil of wire inside a magnetic field. Alex, go ahead.
In my house, we have this one flashlight.
Okay.
In order to get it to light up, you push it
Yeah,
back.
same
I
thing.
as a child because I was like, I'm
Now-
too lazy.
So now, that's, yes, okay, it's not necessarily convenient to use quickly, but the one thing that it doesn't need, though, is what? It doesn't need batteries. It doesn't need a voltage source, because you are creating the voltage, so you are creating the current by changing it's a loop of wire that's attached to it. Or, if you ever seen, there's another kind, Alex, it's the same sort of setup, but instead of cranking it with your hand, you shake it back and forth. Has anybody ever seen this?
Oh, wait, I remember doing
You
it.
shake it back and
It's
forth.
like in this little thing.
Yeah, and there's a little piece of metal inside that goes back and forth. that little piece of metal is a magnet. And by shaking it back and forth, you're moving the magnetic field, and that causes the current inside of the flashlight, and that's how it works. So you can, like if you hold the on button and you shake it, you'll see the light, and it goes on, off, on, off, on, off, on, off, because as the magnet moves back and forth, it creates current, but when it gets to the other side, the current stops. But if you don't hold it on, it has a device in there called a capacitor that stores that potential energy and then releases it when you want to release it. Same idea. There's a magnet, or there's a coil of wire moving around a magnet, or a magnet moving around a coil of wire that produces current. Okay? Those are both small scale applications, but we, or our society, pretty much runs on a big scale application of the same exact thing. So over on the right hand side, you have the picture on the back of your outline. This is a picture of an AC generator. The right hand side of this picture, you'll notice, right, green up on mine, right, this is the electric generator. The electric generator has two parts. One, there is a big, strong magnet that surrounds it, or several magnets that surround it. That creates a strong magnetic field. And then inside the magnetic field, there is a big coil of wire. It's actually several coils of wire. Those coils of wire are attached to this piece right here, which is called a turbine. But really, a turbine is just a fancy name for a fan. If the fan turns, it turns the coil of wire inside the generator. And if a coil of wire turns inside of a strong magnetic field, we get current. The generator, the setup of the generator, is exactly the same as the hand crank generator, or the flashlight, or the bike at the Science Center. It's just a bigger scale. Go ahead, Julie.
But how come, like, with this giant generator people use, why do they make so much noise?
Because most of that noise comes from how we get the turbine to spin around. Okay? So, how you get this turbine fan to spin the coil of wire is what kind of a power plant it is. Okay? At Niagara Falls, there is a large power plant because leading to Niagara Falls, there is a river that moves relatively quickly, right? You stick the blades of the fan in the river, and guess what they do? They spin, and that spins the wire, and that generates the electricity. That's a hydroelectric power plant. I've been trying to. I fixed it a little bit this morning, or earlier today too, I think. So. But not every place has a reliable source of water that flows quickly enough to turn the turbine. So sometimes we have to turn it artificially. Most power plants, as you can see here, is labeled up here, right? Work on steam. And steam runs through this pipe, and we use basically the steam like a hose, and we shoot the steam at the turbine, and the turbine spins. Where that steam comes from is also determines what kind of power plant we have. In Avon Lake, there's a power plant. It's on Lake Road, if you ever take Lake Road West. Okay? Yeah. Go back. Yes, go to Miller Road Park. Yeah, anyway. If you go past there, you can go right, you actually basically drive right through the power plant because that power plant relies on coal. The coal heats up water, that turns into steam, that turns the turbine, that spins the coil, that creates the current. A nuclear power plant, which this is actually a picture of, uses the energy released from a nuclear reaction to heat up the water, turn it into steam, spin the turbine, spin the coil, create the current. The setup is exactly the same as the crank flashlight. It's just on a bigger scale. We turn the coil of wire inside a magnet, or we move the magnet around the coil of wire, which is the shaky flashlight, but it's the same thing. That's where the current comes from. So, an AC generator uses mechanical energy, usually the kinetic energy of moving steam, to turn that coil of wire within a magnetic field. And as the coil turns, it produces current. But a different kind of current than a battery produces in a circuit. Okay, and we'll talk about that in just a second. So it produces moving charges, but a different kind of moving charges. Okay so far? You can say no. Basically, is the wire moving around a magnet? That's what causes the current. So here, in this generator, there's magnets that surround the outside, and inside there's just a wire that spins around in a circle. And that's where the current comes from. That's the gist of it. All right. Remember that I told you you wouldn't be responsible for this, and you really won't, but the current is only produced when, we're back on the front side now, sorry, back on the front side of today's one. Okay. The current is only produced if the wire moves perpendicular to the field. Now, like I said, I'm not going to hold you responsible, but think about it this way. Okay, here's this here's the black, the black weight. Okay, depending on how I move it, I could change its potential energy, or I might not change its potential energy, right? If I move it this way, up, what happens to its potential energy? It increases. But if I move it sideways, stays the same. So there are certain ways we can move an object to increase or decrease energy, but there are certain ways we can move it that it doesn't do anything to the energy. Good? So, a coil of wire goes in a circle, right? So, here I am, coil of wire, right? Sometimes I'm moving this way. 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 Gotta get the locomotion. You know what? People watching the recording will never see that. So. You guys all will, though. So no, I didn't do the locomotion in any of my other classes today. But totally. But the way you guys are looking at me determines how I'm moving in relation to you, right? Here, I'm moving towards you, but parallel to the way that you're looking. Here, I'm moving perpendicular to the way that you're looking. Here, I'm moving parallel, but in a different direction than I was before. Here, I'm moving perpendicular, but a different direction than before. Does that make sense? Okay. When that coil of wire is spinning within the magnetic field, same thing. Sometimes it's going with the magnetic field. Sometimes it's going perpendicular to the magnetic field. Current only gets produced in certain situations. Perpendicular. But perpendicular this way and perpendicular that way produce different motions. That different motion results in the current flowing one way, then the other way, then back the first way it came, then back the second way it came, and it just keeps switching back and forth and back and forth and back and forth. And we refer to that as alternating current. Write these down. You have to understand the gist of it, okay? As the loop of wire spins within the magnetic field, current is produced when the wires move perpendicular to the field. So in this case, that was flat in this picture up here. Go ahead, Julie.
Okay, so let's say Audrey and Steve are magnets
Okay.
at either end, and then Eddie and the other end.
Okay.
Eddie.
Thank you. Thank you.
Eddie and the Jets. Anyway, carry on.
I don't have a one direct current. We can't do that.
So like they were like the wire basically. Would they be like one wire like wrapped up like
Yeah. Yeah, and so they would spin like this, right? Like Eddie would end up where Kenny is, and Kenny would end up where Eddie is, and Eddie would end up where Kenny, and then Johnny, because he's in the middle, really wouldn't go anywhere. Right? But that's why, that's why it's a coil. You know what I'm saying?
Oh, okay.
Like, they would be part, now, if Johnny moved here, right, and then we had Megan as part of the coil too, right, the four of them rotating like this, that would be like what the coil is, that's spinning around. Does that make sense? Yeah, actually physically moving.
It's like we're like wrapping it around something.
Well, no. It's set, and all we're doing is just spinning it in a circle. Like here. Oh. Are you saying how does it keep spinning without getting wrapped up?
Yeah.
Okay. This picture sort of shows that, okay? This is the coil. This is the four of them going around in a circle. Okay? But, right? As let's say they all held hands, all right, and did Ring Around the Rosie, okay? So
Hey, how'd you know it was?
yeah, I talked about plague, yes.
Are you really kidding me? No, wait,
Look.
It sounds like one of those Geico commercials, those new Geico commercials.
Oh, yeah.
So, the reason how, the way it works is, the way it doesn't get twisted up is, so they're playing Ring Around the Rosie, they're all connected together. But, people on the side, okay, let's say they were all connected with one hand and they were playing Ring Around the Rosie, but the other hand they had out, like, as they were going around the circle like this, okay? And another person would stand on the side, and every time they came by, they would slap five, right? Does that make sense? Those are conductors, and so they can keep spinning in a circle, but this is where the current flows out of the people that are standing on the side that are slapping five every time they go by. So it doesn't get like, I see what you're saying, like if it's a coil, well, it can only spin so much before it stops, right? But if you have a part that's spinning and another part that's like connected to it that doesn't spin, and they just kind of like go around in a circle like a carousel, and somebody's standing on the outside of the carousel, right, slapping five with everybody who goes by, right? That's how it can keep spinning and not get all wrapped up. Does that make sense? Okay. So. Yeah, it just goes in a circle, right? And then, like here, like Audrey in this picture right here, this is the carousel that's spinning around. This is the people slapping five, and that goes to the current, and then it goes back. So you would have to have like somebody else on the other side of the carousel, right, that would connect the circle, basically. Okay? So, the gist of this part here being that depending on which way the coil is spinning in relation to the magnetic field that it's acting under, sometimes you get current, sometimes you don't. So, think about it this way. So, if Audrey and Steve are the magnets, the field runs this way. Okay? So, as they're playing Ring Around the Rosie, right, we would have somebody standing by Audrey with their hand out, and somebody standing by Steve with their hand out. Do you really want? Do you want me to demonstrate?
Yeah.
It's like this, but Kenny's all like this.
Well,
Like, I don't
when
know.
Kenny's going by. Okay, here. Do we really want to demonstrate this? Okay.
Making it happen.
Do you want to be part of the Ring Around the Rosie?
Nope. Nope.
All right. Stay there. Yeah. No. All right. So Steve, you're over here. Okay. All right. Let me. Will you like be part of this? Okay. So you guys can stay there. So you can stand out. Okay. All right. So. All right. Ring around the road. Not you. All right. So you four. You get a circle. Okay. Now. Oh no. Sorry. Sorry. Wait. Yeah. Put left hand in the middle. That's hard. Okay. So left hand in the middle. All right. And then your right hand's going to be out here. Okay. Now. Okay. So. Steve and Audrey are the magnets. They don't go anywhere. They stay where they are. Right. But they don't stay like stand up like this. Okay? But the field runs from here to here. Okay? So right now, the way Kenny's moving, he's moving parallel with the field, and Gianni's moving parallel with the field, but Megan and Eddie are moving perpendicular to the field. Does that make sense? Yeah. Okay. Alright. Okay. So, where Libby and Kelly are, right, that Eddie and Megan are moving perpendicular to the field, so they're creating current there. But where Johnny and Kenny are, they're not creating current, so we don't have to have anything there to conduct the current away because they don't have a current, right? Does that make sense? Yeah. Ready? Go. Current. Now, ideally, Gianni and Kenny would be hitting hands at the same
Johnny's
time.
just slacking back there. Johnny, walk faster.
Does that make sense?
There you go.
Wow. Are you serious? I wish you were.
She can save it though. Oh, our current couple. He's recording it.
I'll record it.
The recording people are probably like, what?
I didn't sign the permission slip.
I won't post it online. I just want to have it like a feature. I got to get the whole thing in. So. Oh. Unfortunately, camera has stopped. I need a new phone. All right, ready?
Yo, give me your number.
Wait, hold on. Okay. All right, ready? Go. Good job, everybody. Well done. What? I really wish, like sometimes I have these moments, and I really wish someone was here to see them, other than you guys, obviously. I'm glad you guys see them. But you guys don't write my evaluation at the end of the year. That's kind of a good question.
Wait, can we like have interviews with the principals and say like what we like about the
Oh my God. I'll write a story about it.
Mr. Planisek had a really good idea one class. That one time.
That one time, it was
Yeah,
great.
only once though.
So,
Well, he also lets us know what the top charts were in 2000. And his daughter was born to the song Umbrella.
it wasn't on when she was actually born.
Oh.
Just when we were driving to the hospital that morning. So. Although, if it was on when we were driving to the hospital in the morning, it was probably on like 17 more times during the day.
Umbrella.
Umbrella? Are we on?
Those that aren't even in the box.
Are you really? That has to be more of an organic discussion. I can't just be like, hey, did I tell you about the time I worked with the Yeoman Factory? Now, see, I would like to point out that that demonstration comes directly from your questions, right? Like, I don't do that demonstration if you guys don't ask the questions, right? So the more questions you ask, the more things I can come up with to try and illustrate it. What?
No, we're still recording.
That's good. I'm glad you understand.
I didn't get it when you were just It's recording.
But did that help though?
People listening to this.
All right. So what happens is, right? Okay. Ultimately, the end result of this generator is that we get a current, but that current changes depending on which side of the coil that you're on. The current that comes out of Libby's side of the generator is different than the current that comes out of Kelly's side of the generator. Because they're going different directions. They're passing Libby this way, but they're passing Kelly that way, right? And that's why it creates different direction of current. It's still current, just different direction. Okay? Good there?
Yeah.
This is the one in the back, right?
It's at the back, yep. All right, so Monday, we will be down in the computer lab looking at these things on the simulation. Don't forget, I put up the objective sheet for the test. You can either get it on Tuesday's review day or Wednesday's test day if you want to start looking at it over the weekend. All right? Good questions today, everybody. Have a good weekend. I'll see you on Monday.